Computer is not fixed yet. But they give me hope. So I just have to wait. Order parts, got to get here. Then they got to do it. Then I get it. Restore it all back, you know. All right, we're on electric current. We're moving now. Today we can look at more at circuits. We've started them, but let's understand more what's going on in a circuit as those charges are flowing around. We got to voltage, which is electric potential. Remind us of what that was. Or does anybody remember? That is energy per charge. So voltage was electrical potential energy per charge. So this one. To remind you, so we have them up here for reference, the electric field was force per charge. Thus, the force on a charge, it's accelerated by the electric field. That's what gets them moving. There's something we're poised for this step. If yeah. Right. We did this before too. The electrical potential energy that's gained by the charges. We said voltage is that energy per charge. Well, how much energy is that? What made us change energy before when we dealt with gravitational potential energy and kinetic energy? How did we change? What had to happen? You changed its position or speed. And what actually physically made that happen? What did you have to do to that object? Work. So it's the same, again, I want to emphasize with charges. You have to do work on them to change their energy, to change their location or their speed. So this gains, it's the work done on it, which was force times distance. There's our force times the distance. We did that before. That's the electrical potential energy per charge that those charges get. Well, take this Q and divide it. So on this side, you have electrical potential energy per charge. That's the voltage. It's defined as that. We just said that. But what's left on the right-hand side? ED. So there's two ways you can think of voltage. Again, it's the same thing as electric potential. Electric potential and voltage are the same thing. It's energy per charge, but you can visualize it with this electric field a certain distance away. You're like, yeah, so what? So, example, you got a 9-volt battery. You got your two terminals. The difference between those is 9 volts. But the two terminals are a certain distance away. What? Let's call it a centimeter. Remember, there's an electric field here. Which direction does the electric field go? Right. Take your positive test charge, put it near those. Which way would it go? Yeah, away. It's repelled from positives and attracted to negatives. So your electric field's in that direction. So you can see this electric, or at least visualize this electric field over a certain distance, about a centimeter apart. Well, that's this, the electric field, centimeter apart. That tells you the voltage. If we could take those same terminals from the same battery and just move them farther apart, what would happen? Yeah. We're not changing the battery, so it'd still be 9 volts. But we just moved the terminals further apart. This increased. D gets bigger. So the electric field in there would have to get smaller. Hopefully that makes sense, because that'd be like, now they're further apart, bigger D. There's more space in between. The electric field is weaker for the same voltage. Another example. How about a fluorescent bulb? They often run off of the power in the building, so it's about 120 volts across that distance. I don't know, let's call it L. So again, you got your two terminals. There's an electric field inside. Let's say this is the positive side and this is the negative side. So the electric field inside is in that direction. That's how those are related. That electric field inside there is the 120 volts divided by that L. They are apart. So think about if you had a shorter fluorescent bulb or a longer fluorescent bulb. That's changing the D. And so the electric field would have to change inside the bulb as well.
So the shorter the bulb, the more,
Well, yeah, let's see. Electric field is V over D, guide to everything. So for the same 120 volts, with a smaller D, the shorter bulb, yeah, the electric field inside would be larger for a shorter fluorescent bulb.
But the voltage is the same.
Well, in this case, because we're hooked up to the same power supply, yeah. You can look at it that way. If you change the, if you maintain the same electric field, let's say that stays the same, then a shorter bulb could be lit with less voltage. You don't need as big a push to get the shorter distance for the same electric field. But fluorescent bulbs are usually rated at a fixed voltage. That's why I did the first example first. You got to keep one constant to see how the others change. So, but I just wanted to make this connection because we mentioned that energy per charge. But how does that relate to that electric field we talked about and introduced? That's how.
So the capital E stands for electric field?
Correct. The capital E is electric field. So when you go around a circuit, you use up energy. It goes through a resistor, you use up energy. So the voltage drops. It decreases. That means each charge has less energy. You've used up some of the energy. The voltage goes down. When you go back to the battery and through the battery, oh, you gain energy. The voltage goes back up. You get pushed around again. It's all conservation of energy, is what a circuit is. Now there's a thing that hinders you as you're trying to go around. The current. Remember, that was the flow of the flow of the charge. The flow rate, how much charge goes by in a certain amount of time. Well, how much is going to flow in a circuit? That's proportional to the voltage. If you push harder, what do you think happens? Yeah, it goes further. Or I mean, there's more charge that can flow in the same amount of time. Current goes up. So those are directly proportional. Now think about your circuit. You're trying to push charges through something. What if it's harder to get through that something? what happens? You won't get as much. We call that something resistance. And it's inversely proportional, because if you increase the resistance, less charge can flow. Does that make sense? Think of, the analogy is not always perfect, but it works pretty well. Water flowing through a pipe. I think, did we mention that Wednesday? Water through a pipe? Somebody help me. I've taught like 3 other classes since Monday, or Monday, and I forgot who I told what to. So I apologize. Well, anyway, water is like the charge flowing through. Let's do it then. Picture it. How do you move water around in a pipe? Pressure, a difference in pressure. And what's going to create that difference in pressure? What'd you say? Thought I heard it. A pump. So I think of a battery or a power source as a pump. It's what's trying to push the charge around to get it moving, to establish that electric field in the circuit, because it's the electric field that makes them accelerate. So think of voltage as a pump, trying to push water around. Water is like the charge. Charge can flow. How much water is flowing? That's the current. The rate at which the current goes, the water or the current goes, the flow rate of charge or the flow rate of the water. That's the current. And that's what actually moves around in the circuit. Remember the circuit we made? The charges were already in us. We just closed the circuit, saw both sides of the pump, the battery, which made those charges, hey, start moving, forward march, and they all started moving together. Do you remember drift velocity? Yeah. Those charges actually aren't whizzing around at the speed of light. The electric field's established at the speed of light. And then all those charges that are already in the circuit start moving together. And they start getting accelerated, let's say that way. But then they run into other particles and they bounce back. But the electric field's still trying to accelerate them. So, you know, they're hot and they got a temperature and they're moving around, they hit things and bounce back, but over time they kind of drift. You remembering this now? Me looking like a dork like this? So the charges aren't moving that fast, but they are moving. That's the flow of charge. That's the current. And it's that electric field, that difference in voltage from the two sides, that's trying to push them through the pump. The water wouldn't go anywhere unless you had a difference in pressure caused by the pump. Now, make the pipe narrower, skinnier. Do you think it's harder to get water through or easier? Harder. That's resistance. You've increased the resistance. So that's why it's inversely proportional. Putting this together is Ohm's law. I is defined as current. The flow rate of charge. And just friendly reminder that if you're sitting there going, I'm confused. That's why I assigned the book also. It explains it. I explain it. Hopefully the demos help explain it. The homework questions try to walk you through and think of it different ways. So if all you ever do is just listen to me and lecture, you're doing a disservice to yourself. The book can explain it too, and it might ring a bell better the way he words it. Plus, remember, I don't get things. I don't pick things up. I don't retain them or necessarily understand it the first time I hear it. So it's good to go over it. The text also has some check your understanding questions with explanations. Because I realize this stuff can seem a little more abstract, trying to visualize what charges are doing inside wires and resistors and things. So current is proportional to the voltage and inversely proportional to the resistance. You rewrite this. Those all say the same thing. This is actually how resistance is defined. If you have more resistance, then you got to push harder to keep the same flow. Or if you want more to flow, you got to push harder for the resistance. If the resistance is less, you don't have to push as hard to have the same amount of current. Yes, resistance would be like a skinnier wire. Just like water through a pipe. You constrict the pipe, the resistance increased, and you have to push harder to maintain the same flow rate. If you keep the same push, then you won't be able to send as much through as fast. So same with wires. If it's skinnier, there's more resistance. If it's wider, it's like it's easier to get through. There's less resistance. It can. Oh yes, Bernoulli's principle. It maintains. It would have to maintain the same flow rate. In order, yeah, this idea. That's a good thinking man's question. Charge flowing through and it all constricts down into here. Bernoulli's principle with fluids, we realize that when it goes smaller, there's a corresponding increase in the velocity, and thus a corresponding drop in pressure here. That's if you can, how should I say this? In an electrical circuit, it's like if you're going like, well, same thing, I don't have to redraw it. The charges are crammed in there. If it didn't speed up there, then things would start to back up. Once they start to back up, it's putting a back pressure on. And your pump can only work so hard. So if your pump can only do so much, then it backs up and the flow rate slows through the whole thing. If your pump can keep up, then you're right. It'll speed up there. It can maintain that flow. In order to maintain the same current, the same flow rate, it would have to speed up there. That's what we did with the air in that tube over here. The continuity equation said to maintain the same flow rate. Since less is in here, it would have to speed up to get past this section in the same time it does this section. Otherwise, it would back up. In terms of currents, that means, or charge, that means the flow rate of charge, thus the current, which is the flow rate of charge. If that were to stay the same, maintain that rate, you just increase the resistance, it would have to go faster. How do you make it go faster? You'd have to increase the voltage, the push, in order to do so. And that's a perfect example of Ohm's law, that relationship between voltage, current, and resistance. And electricians use that over and over again in all types of circuits. It's a nice, simple relationship, but works practically everywhere. In any of these, they're saying the same thing. I want to show you a little more of that relationship here. So basically, this is like my power supply. It determines how much voltage I can send to this circuit over here. Basically, it's a resistor right here. Current comes in the top over here and out the bottom over here. So if it comes in the top, it comes along this bar, because it's a conductor, down this, and through these coils of wire. That's creating the resistance, and then out the bottom. if you increase the length of wire by doing this, see, now it has to go through all of this wire, more wire. Do you think that's more resistance or less resistance? You're right. A longer pipe, more wire, more resistance. If I move this way, decreases the resistance, less wire. That's what I'm going to do. This is going to measure the voltage difference, the difference in voltage, the difference in energy per charge from one side to the other. Because as it goes through this resistance, it's going to use up energy. It takes work to get across the resistor. So those charges will lose energy, which means they'll have more energy on one side than the other, a higher voltage on one side than the other. The voltage will drop, and this will tell us what that is. This will measure the current through that resistor, a representation of the flow rate. All right. That's on. Flip the switch. There we go. We got some values. These are arbitrary. You can see the voltage. You can see the current. Well, the ratio of V to I, V over I, that's the resistance. I can take this value, divide it by this value, and that tells me how much resistance is in the circuit. That's Ohm's law. So what do you think, wake your brains back up, what do you think will happen if I increase the resistance? Make it go through more wire. It'll require more voltage? Because it's harder to get through? Let's see. Well, before I do that, okay, that's one answer. Any other thoughts? I'm going to increase the length of the wire. I'm going to make it go through more wire, thus more resistance. Right. What do you think this one will do? I heard all three answers.
Depends on what happens to the voltage.
Now this can be a little confusing, so I'll clarify one thing. In this circuit, yeah, I guess I should specify. I got two voltages going on here. So, yeah, let me clarify. We have the voltage of the battery, what's trying to push the current through. That's this.
The left or the one on the right?
Yeah. You know what? Because I got two things going on here, it can seem more confusing. This is a fixed voltage. This is what's actually trying to push the charge through our resistor. This is simply just telling us how much the voltage changes as it goes across the resistor. Yeah, so let's do it and see what happens and then make sense of it instead of just shooting in air here. You ready? Let's watch this one. You thought this would increase? If we increase the resistance, it'll be harder to get through. So if this goes up, that means that's telling us it's using up more energy to get across. Here goes. It did increase. So yes, more resistance, harder to get through. It takes more work. You're going to use up more energy. So this resistor used up more energy and had a bigger voltage drop across it. What did the current do? I increased the resistance? It decreased. Let's make sense of that. Make sense of that. If you got more resistance for the same push, what's trying to push it through? So that's not changing. You increase the resistance. Is it harder to get through? Yes. So less went through. We saw that decrease. That's Ohm's law. So less current flowed through a bigger resistor, but because it's more resistance, it uses up more energy. And you could see that. Does that make sense? Yes? That was the only thing that stayed constant. What's trying to do the pushing, this voltage. Because, again, from here, it's less resistance. So you have these values. This is using up this much energy. If you increase the resistance, it uses up more energy to get across because it's harder to get across. You have to do more work. So we see a bigger drop in voltage across the resistor. The current went down. Did you see that? There it is. Increase the resistance. It went down. Again, because this is more resistance, it's harder to get the charges to flow through it. For the same push. Remember, this is what's doing the pushing. So for the same push, same voltage, more resistance will have less current in it.
So is that the V equals IR and it's like, if you make the I bigger, then the R has to be smaller in order for it to stay the same, or if you make the R bigger?
Yeah, let's relate it to this. Let's relate it to this now. I increased the resistance. The voltage across the resistor went up. The current went down. That agrees. That makes this ratio bigger. Yes? Now let's apply it again in a separate occasion over here with the current. What was going on there? And the voltage of the battery, the power supply. That voltage is fixed. The voltage is trying to push it through the resistor. This is the beauty, but also the confusion of Ohm's law. It works everywhere as long as you just understand what's going on here, and understand what's going on here, and understand what's going on here. You can apply it in each of those situations. It's when you try to apply it here but consider this stuff, well, that's not accurate over here. So again, for the voltmeter, increase the resistance, used up more energy. We also saw less current go through it, but that agrees. This ratio got bigger. Now for the power supply. The power supply did not change its voltage. It's still pushing the same. So if we increase R, which we did, that has to be less. Less current can flow in the circuit. And we saw that. So it all agrees. Does that help? The beauty is now, if you have that, you can understand about every circuit out there. Let's go back to here, and I'm going to change it up. This time, I'm going to change this voltage. I'll decrease it. I'm going to decrease the push. What do you think will happen? It'll be equal to this one?
So it'll be the same as when the earth resistance.
When there was more resistance, that went up, and this went down. So that's what you think will happen when I push harder. Any other thoughts? Yes?
I think both will decrease.
Both decrease. Why?
Because it's the ratio. So they have to
Oh, the ratio. What ratio?
R equals V over I.
Yeah, this resistance is V over I. Am I changing this? No. It's the same resistance. So that ratio has to stay the same. So they could either not change, both increase, or both decrease. But the ratio is the same. Very good. Because that's what resistance is. It's that ratio of voltage to current. I'm going to push less, so you thought they'd go down. Any other thoughts? Okay, let's do it then. You ready? I'll decrease the voltage, and they both went down. Right. I'm pushing less hard. So that means less current flows. And if there's less current flowing, then there has to be less voltage used up across that resistor to keep that ratio the same, because I didn't change the resistance. Again, let's increase the voltage. You should see both those increase. But the ratio stays the same. These are not accurate values. They're just a representation. The actual values do work out. This is actually a fifth of the actual reading, and this one is actually twice the actual reading. That's why one looks like it moves greater than the other one. Otherwise, we blow the circuit. So decrease, they both go down. Increase, they both go up. This is the push. Questions? All right. Let's move this out of the way so you can see the other things. Let's continue to apply Ohm's law on a few things then. Let's do some circuits. Let's hook some things up in series and parallel. So here's my power supply, a 12-volt battery. I have a resistor here to limit. I'm going to provide resistance to limit how much current can actually flow into my circuit. Because if I let too much current flow, I can blow these light bulbs. So I'm using a resistor to limit the current. So for a fixed voltage, the battery, 12 volts. I increased R, so I'm going to get less current in my circuit, just to protect my light bulbs I'm going to connect up here. So there's an application of Ohm's law. Here's a 12-volt light bulb. Hey, turn around so they can see you. There it is. Pretty exciting. How much current's flowing through it? Well, 12 volts divided by whatever the resistor of the lamp is. That tells you how much current's flowing through it. What's the unit of resistance? Anybody know or read the book? Yep. Resistance is measured in ohms. Whoops. It's the Greek letter omega. Whoop. Ohm's law. Same guy. And there's some dumb puns you can do. Let's see. If that's an ohm, what is this? On wheels. It's a mobile ohm. What is, let's do, that. An umbrella. All right, you're getting the hang of it. What is homework? Good job. Oh, you can Google these. There's all kinds of dumb puns. So. Because work is force times distance, so it's homework. All right. So we got that one. Let's hook up another bulb. You guys deal with circuits, plug things in all the time. That's why I made sure to cover this stuff. Let's do two in series. They're in series because there's only one path through the circuit. It has to get through this bulb and this bulb. What do you think? Whoa. What do you think will happen? Yeah, they're meant to be the same light bulbs, same resistance. Half as bright. Why? What did we do to the resistance in the circuit? Did it increase or decrease? Right. It has to go through twice as much. So you add up resistors in series. It's this resistance plus that resistance. Twice as much resistance. Twice as much resistance. So what happens to the current? for the same push, same 12-volt battery. Half as much current. Let's see if they're dimmer. Yes. And a third one? They're even dimmer. Yes, they're each get a third. That's what they were. Good. Now, in series circuits, this one's a little harder to do, but if you have everything hooked up in series and one bulb goes out, let's say this bulb goes out. That's what happens. There's a break in the circuit. It can't get across. These don't see, the electric field isn't established. You can't see both sides of the battery. No current flows. This is like infinite resistance. So if one thing goes out, they all go out. Let's hook some things up in parallel. We had this one. It was nice and bright. What will happen if I hook this one up in parallel with the first? Why would it be the same brightness? There's a different path. The current splits. It comes along here. It can go this way or it can go this way, both of which can get it back to the battery. So yeah, it has a choice. So why would it even go this way? Right now it's infinite resistance. Don't start thinking because it's closer to the battery. Remember us in our circuit? We all felt the same at the same time. So as soon as I connect the circuit up, charges here and charges here, they all feel the electric field and will start moving together. They are the same brightness, nice and bright. Somebody said it. What's the difference in voltage across this bulb? 12 volts. What's the difference in voltage across this bulb? 12 volts, because it can see both sides. No energy. It's always conservation of energy. Comes along, nothing. Oh, now we use up energy to get through this light bulb. Whoosh, and back. Gain the energy back, go around again, so to speak. But the same thing can happen up here. It's still 12 volts drop. It's 12 volts difference across this bulb. So they're the same brightness. If I added a third, it would be the same brightness. Let's do, though,
So if you kept adding light bulbs, they would all be as bright, but with your battery, you would use up the power in your battery faster?
why do you think it would use up power in the battery faster? And that is absolutely correct. It is because you're powering more light bulbs. Hooking up in parallel is nice because they're brighter. And if one goes out, the other two still have a path. They don't go out. That's nice. But the downside is, in order to have these all be as bright, there's actually more current flowing right here. In order to provide that much power for each bulb, the battery has to work harder initially to pump more current out. Let's look at that. Same voltage. Our 3 resistors hooked up in parallel, but more current's flowing to keep them that bright. If this is bigger, what does that mean the overall resistance is? Less. When you hook resistors up in parallel, there's overall less resistance. This is like a wider pipe. Can you see that? If you just have one skinny pipe, now let's widen it. And we got 3 paths. It's easier to get through. So more current can flow out of your battery. And it does. But that means it costs you more too. To power these 3 the same as one, you're going to use up more energy. Your battery will drain faster. It'll cost you more money than if you had all 3 hooked up in series. Because in series, they all got the same current. They were all connected. It had to get through one before it could get to the other, before it could get to the third. Like this. So in series, let's write this down for you to summarize. And we'll have over here parallel. That's a symbol for resistance if you hadn't figured it out by now. This is the symbol for a battery, voltage. R, 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 R. So in series, you have to add the resistances. As you keep adding a resistor, the resistance goes up. The overall resistance is bigger. It's actually R1 plus R2 plus R3. You just add them up. But if you have more resistance, what happens to the current? Goes down. So there's less current flowing here. Less I than this one. More I flows. There's the I here. Here's the I here. I in series, I in parallel. This has less. This has more. Over here, the overall resistance is less because it's widening the path. It's easier to get through. That's why there's more current flowing over there. Yes? Right. Well, some Christmas lights. So if you have a string of Christmas... Go ahead, Court.
I was actually about to mention that, like, because on some Christmas lights you actually have 3 wires, so it's a combination of series and also parallel connection.
Yeah, most modern ones there's a combination of series and parallel now.
So only like half of your string goes
Yeah.
and then half is something on which bulb.
So if they're all in series and one bulb goes out, they all go out because there's a break in the circuit. Then you know they're all series. If only a section all goes out, then just that section's in series. But that section must be in parallel with another section because that section didn't go out. So like here's a section that goes out, but the other section still can get power. If one goes out and only one goes out, then they're all in parallel. So does this part make sense? You tell me. Well, now I can't see both sides of the battery. They all go out. Current stops flowing, period. So how would you want to hook up car headlights? Yeah, parallel. Because if one burns out, you don't want to be completely blind. There's one other thing to note here. Here, well, you told me on this one, each one sees 12 volts, right? This is all, we haven't used up any energy getting to those resistors. But now, we use it up. All of it. So they each get 12 volts. So in parallel, another thing to note is, it's all the same voltage across each resistor. That's why they were equally bright. They used more power, more energy. Voltage is energy per charge. If they get all the 12 volts, then they can use up 12 joules per coulomb of charge. Over here, what do they have to do? Exactly. They have to share the voltage. If they're identical resistors, they each use up 1/3 of it. So what would the voltage drop be across each resistor? 4 volts. This would use up 4 volts. This would use up 4 volts. And that would use up 4 volts. Go back to the battery, gain energy, and go around again. Yep. Exactly, because there's 3 paths here. That means this has to be bigger, because the current has to split over here. They share that current. The current that comes out of the battery splits 3 ways. So you've got to start with 3 times as much. Over here, they all have the same current. Because they're just one after another. It's like water flowing through the pipe. The same flow through this resistor is the same in this one and this one. Now overall, this has less current. It's just the same for every resistor. Over here they have to share it, but you start out with more in the first place. This will help you with some of those circuit questions in the homework and or the exam or whatever. But that's all from Ohm's law, how these are related. Should we try a more complicated one in the last bit? Then I'll burn some stuff Friday when we review. Let's see, I don't know, I'm making it up here. How about two in series in parallel with one? You can make up all kinds of things. What do you think will happen? These two are in series with each other. So they have to have the same current going through them, but they share the voltage. This, the current's split, but it gets all 12 volts. These get 6 volts. These get 3? If they all had it. However, remember when we just had 2 in parallel? Across this one is 12 volts. Across this is 12 volts. So he gets all the 12 volts. They have to share it. Very good. He's brighter. It's using more energy because it got more energy. Good job. Questions? One more then. By the way, why don't I die when I do this? Ah! Oh, no, just... I am grounded. The voltage is 12 volts. Ohm's law determines how much current goes through me. What else determines how much current goes through me? My resistance. And I have a lot of resistance compared to these light bulbs. So very little current goes through me. This is not capable of pushing enough current through me. No. Now, if this is hooked up in your circuit in your car and you touch improperly grounded, don't do that. Don't do that. I don't want to misinform anybody. All right, what's going to happen here? We got these two are in parallel, but this combination is in series with this one. Little harder. Well, these together are in series with that, but these are in parallel with each other. Now, so across from here to here, there's 12 volts. So let's just simplify. Let's think of this as 1. So this is going to get 6 volts. Well, maybe it'll get 6. This has a certain resistance R. What's this resistance? They're in parallel with each other. Less resistance over here. It's wider. Less resistance. More resistance. Who will need more energy to get through? The more resistance. So this will use more of the voltage, which means it'll use more energy. I expect this one to be brighter than these. But how will the brightness of these two compare? The same, because it can split evenly in the two. Let's see. Yes.
Oh, they are there. Okay.
So this one is brighter. It's got more resistance, so it's using more of the voltage. These are using less, a lot less, because they're in parallel. There's less resistance combined here. But because they're in parallel, they each get the same voltage. Questions? All right, seriously, go review the answer keys. Past videos, your book, whatever. Come with questions and concerns, and we'll have a good review Friday. See ya.